Bismillah ar-Rahman ar-Rahim, and welcome to, I think it's our last seminar in this semester. And today we have a very interesting topic. Our speaker is Dr. Mirza Pasovic. I'm sorry if I don't pronounce it correctly. He received his bachelor degree from the University of Mirza in Slovenia. Correct? I hope I'm pronouncing that correctly. The work he performed during his undergraduate was published in the EMBEC conference, and as a result, he got an offer for a PhD in University of Lyon 1. The main investigation of his PhD work was on ultrasound imaging, specifically ultrasound contrast harmonic imaging. And after after receiving his PhD degree, he worked for medical imaging companies in Canada in the R&D departments, mainly in hardware. Today he will talk about his experience, and he promised to give us first semester next year a seminar regarding his research work. Please.
Assalamu alaikum. Thank you very much for the introduction. Today's work will be mainly about my experience in the industry and what I did in the industry. I think it's still going to be very interesting. So I'm going to be talking about multispectral and fluorescence imaging that I did. So I'm going to talk a little bit about multispectral imaging. Why do it? How did we do it? I'm going to show you the results that we obtained and also the device that I built. And also the same kind of path I'm going to be following in fluorescence imaging. Why, how, and I'm going to introduce a 3-chip camera that I started building. So multispectral imaging, why? We know that basically light is just part of electromagnetic radiation. That's what it is. Just electromagnetic radiation. It starts all the way from gamma rays down to very, very long waves. And here, very small part is where human eye actually works. From everything, only a small part is where the human eye works. And in there, if you look at the solar spectrum that comes of the visible light from the sun, what we notice is that it is not constant. You see that there are the lower ones, the lower wavelengths are much less represented than the higher waves, and then again they drop. So it's not a uniform distribution of light. In addition to that, there is also sensitivity of the human eye. Human eye also doesn't have a uniform sensitivity over the whole spectrum. And not only that, during the day and the night, different type of receptors in our eyes kick in. So this is the daylight. For the night light, what you will see is just one peak here and then everything down, right? So all of this together, right? And when we walk into any office or anywhere, we still have our other lights, and even they have very different spectrums that they illuminate. So there is a problem here. What is it actually that we are looking at? This problem arises a lot, for instance, with the people who do dermatology. What they do is they just use a simple camera, take a snapshot, then 3 months later, when it is winter, take another one under completely different light setting. So that's a problem. Are you really imaging the correct thing, or are you imaging something else? So what we decided is to make a device where we are going to control the excitation light. It doesn't matter when you come, in the morning, in the evening, middle of the night, summer, winter, wherever you come, the excitation light should always be the same. And when I say that, I mean we control the wavelength, not necessarily the amplitude, but the wavelength. And how we approach this is that the visible spectrum that we had, we divided it into 18 different wavelengths. Each one of them we illuminated, and then we try to see the result. Here is the device that I've built. So this is a handheld device that you just connect to your laptop. On top, it has two buttons where you just, when you are at the position where you want to be, you scan it. Here, there is a CCD sensor. So my part in this was, and I was taking kind of a lead role here, it was all the electronics and the firmware that's in it, that was mine. I worked closely with the mechanical team so that we can design all of the optics and the supporting body, and a software team, because the pictures, there isn't enough power to do any processing on chip. We did that on the computer. So the 18 LEDs were actually 36 LEDs. The 18 wavelengths, there were 36 LEDs, where to have some sort of a uniform lighting, we would fire on each opposite side the 18 LEDs. They would go around, scan that, and transfer it immediately to a PC where a real-time image was shown. And also on demand, on the press of the button, they would be saved in a folder so that later on they could be reviewed. So basically what it means is, like I said, on the opposite sides, what we had was illumination of, let's say, skin or any sample or anything like that. The reflected light would be captured by the sensor, and then through an FPGA and the USB 3, we would just drive it to the PC for processing, simply because PC has power that FPGA will never have, right? So basically what we gained, right? So if you look here, this one sample that we had, right? As we are scanning from different lights, as you can see, different features come up and also different colors, right? And we went all the way from 450 down to 930 millimeters. And from all of together, a true color image would be put together. So we went, well, not all the way to UV, but we were in the ER also, and then they would be together to form a complete image. One thing that I want to show you, the next one, is if you can just now watch it. This is the same image as these. Only this one is under normal light, and this is after putting all the 18 wavelengths together. So you can see how much more features of this small come up compared to this image. Now, in here, I just showed you something that doesn't have a lot to do with biomedical or something like that, but it's the most, the reason why I chose this is because it's the most representative, right? In addition to just making a true color image, what we did is we also correlated absorption and reflection of different wavelengths to the pathology. So if it is cancerous, if it is malignant, if it is benign, we were also able with combination of which lights and which wavelengths are absorbed and which are very nicely reflected, we could also help the doctor to say, yeah, this should go for further analysis, or no, it's just a normal mole that you get.
Excuse me, just
yeah.
a bit of confusing to me at least. You eliminate the subject with the different LEDs.
Yes.
And the LEDs, they are filters that they reflect over the certain
They are already chosen to have a very small wavelength, to have a bandwidth of.
Okay,
so it's not white light LEDs. They are already chosen to have. They had like at 10 nanometers wavelength, and then we would use filters from Samrock to even push it to like 5 nanometer bandwidth.
So basically, you eliminate with a certain wavelength and you collect the image. You
yes.
don't do anything with it.
Yes.
No filtering on the
no filtering on this.
Only
on the excitation. Only on the excitation.
Just for curiosity, what about if you eliminate with the normal one and then you filter on the image side? Just trying to
if you filter on the image side, the problem that you're getting with this, it's for the handheld device, you have to put in a lot of filters. Yes. There is already a camera like that. It has a huge wheel on the outside, and you have to turn that wheel. So it's not a practical thing, right? This is a little bit more practical, right?
Actually, again, this image looks a little bit dark, but usually you use some techniques for illumination compensation.
Yeah.
So basically, it would get much better contrast than what.
Yeah. If this is, it's actually. I know you think that this is just a little bit more illuminated than here. If we put a little bit more brighter light or something like that.
No, it's just in the histogram. Basically, you have histogram modification on this one.
Yes.
Would make it basic contrast would be much better than this one here. Because here the dynamic range is very much compressed.
Yeah.
So basically, just
if you expand it, yes, sure. But without what we were going for is using these to make a true image without data fudging. Because when you play with the histogram, you are playing with the data. So you are basically adding data, right? Here, there was none of that. These were raw images, raw data that were on the light that was characterized, and based on that, the image was made. But the moment that you are playing with pixels, or any histogram, anything like that, you are adding data. And that's what we wanted. We wanted to do processing on raw pixels. And that's what this does. In addition to that, if you just do the histogram thing here, you will not be able to see what we're looking also when I talked about the absorption of some wavelengths, reflection of the others, how much it reflects certain wavelengths. Those things would not be able to characterize, not from this image. But here we get the whole bundle together, a true color image and a data for further characterization.
The spectroscopic aspect of it, basically, you have the spectroscopic differentiation between different wavelengths.
Exactly.
But actually, when you combine it, you lose this information. So basically,
no, because you still have that. Because we would still have all of the 18 images saved, or they would be on the hard disk saved. They are not thrown away. They're still saved, right? So this is just for the presentation. This is for the presentation and for the visual presentation for the doctor, right? But you're right. We cannot just disregard them. They are still kept on a database. For sure. Actually, the calibration was done on each wavelength, and it was done before using for the scan. So what we had is the white phantom with the total reflectance, and we would illuminate, pick it up. It had the uniform illumination, and that would give us the characterization for that white LED for that particular wavelength in the excitation and the CCD collection. Right, the reception of the CCD. So we would have complete path, it would be characterized. So this is the device that was built, and this is yours truly, that we gave it to the BC Cancer Agency, and they used it. This is Dr. Haishen. He's one of the leaders when it comes to the cancer research, especially skin. And this is our brother Yasser Fauzi. I think our other brother Yasser, he knows him very well. I worked with them closely on actually developing this. They were the kind of the driving force of the research behind it. So another thing that I did is I went today, just now, I went on ScienceDirect. I typed in multispectral, anything. I took out the first one that I did, the first 25 or 24 that I found. You don't have to remember this, the names. What the interesting part is here. If you go, just look in how many different journals multispectral comes up. I think that only infrared physics and technology is repeated twice. Everything else is different. So this is really an imaging technique that is really wide used. It has wide applications. It's not just one thing. You have it in optics, lasers, measurements, remote sensing, food, even in Journal of Saudi Society for Agricultural Science, ore and geology review, artificial intelligence, coastal and shelf science, optics. So it's really quantitative spectroscopy and radiative transfer. So it's really wide range. Technology. It's not just one thing to do, right? So I really hope that this is something that maybe we can start up here and a little bit work on it. So another thing that we did is then fluorescence imaging that I did. So what is fluorescence? It's the ability to absorb light at one wavelength and emit it at the other. So what it means is that when photon hits an electron of the light, when it hits the electron gets excited to an unstable state of energy. It slowly starts losing that energy to excited state, and then when it goes back to the original state, it loses energy. And the loss of energy is in terms of another photon, which is a wavelength, which is a higher wavelength, meaning lower energy. That also gives us the reason why if we excite at the blue light, we get green fluorescence. If we excite at the green light, we get red fluorescence. It never goes the other way around. It doesn't happen, right? So I just wanted to show you here an application, and this is directly from the company that I worked. This is a pinpoint machine. I worked on this machine, and I know what it does. This is a normal white light image. If you can just kind of block this out of your mind and concentrate on this one. When a doctor sees this image, he can pretty much not tell anything about it, at least that there is a lot of slime there. That's about it. But then when he looks under fluorescence light, you see how much here this pops up? All of this, he knows it's now perfused with blood. Just on a white light image, this is not possible. However, when he looks under the fluorescence light, under fluorescence imaging mode, his vision expands immediately, right? So this is just one of the applications that I worked on. That's why I put this one. But there are much more than these, right? This is why it is used. Now, one problem that we had is that this is the camera that we use, right? That this camera has a CMOS sensor here. It's a nice sensor. It's a good sensor. However, it's a sensor that has to be able to sense all the light, visible, and when you go also into near infrared. So what we decided was to have this is the problem. So in camera, there is only one imaging sensor for visible and near infrared, right? So our solution was to have camera with 3 sensors in. For this, we designed a prism that when the light comes in, there is a first reflection of the blue light, the green light will pass, and then there is a second reflection here of the red light. What this gives us possibility is completely independently image the blue spectrum, whatever you want to call that, the green spectrum, and the red spectrum, and the near infrared with it. So my task here was to design the 3 boards, the 3 image sensoring boards, what we call the passive concentrator, where these would be feeding basically they are the control lines for each image sensor. This is SDI 3G. I'm sorry here. It's the output of every sensor that we can immediately see it. This would then be run from an FPGA, and here I wrote a firmware for the FPGA to control all of this. The biggest part was because I was limited here to actually make these work very, very synchronous. If I just go one back here, you have to imagine that the sensors, they lie on these parts here. This is where we put them, and they would do the imaging. The problem, the biggest challenge, the problem in this was that they have to be perfectly aligned. If you know that, for instance, an imaging sensor, it has a pitch of 3.5 micrometers. 3.5 micrometers. So if you are off by 100 micrometers, it's nothing basically, 100 micrometers, that's already losing 30 lines of your sensor in the imaging. You're already losing that. That's just one aspect. The other aspect is because you see that they are all very much in different planes. They are all in different planes. So to align this, you have to have basically 6 freedoms of degree. You have to be up, the forward, backward, left, right, up, down, both tilt and both rotations, right? So because of that, the synchronization here had to be very, very sturdy. This was my part. Actually, when this was just designed, this when I quit to come here, so I didn't go any further than that. But I still did the same thing as before. I went for the fluorescence imaging. Just today, I just put in fluorescence. That's it, just that. In the ScienceDirect, and you can see here, one after another, completely different what do you call it, journals, completely different applications, and really lots of them. I will kind of, my main thing that I wanted to do is, I wanted to remind you what you already know, what you maybe studied a couple of years ago, and maybe you should just repeat, and I wanted to kind of reignite the flame for imaging techniques here. I hope I did that. Please.
Maybe you can use this one so that because for recording.
Okay. About the way you generated the red, green, and blue.
Here.
Why didn't you just use the filters? Just filters, beam splitters and filters, and that's it. Because usually we do that.
Yeah, no. If you use what we wanted to do is to have a full resolution,
okay.
And you wanted also to have real-time imaging by changing the filters, right? You have what you have to understand is that here there is a filtering layer. So when the blue hits, it goes here, but these two go through, right? Here the red is reflected, and then on this way, and the green goes through, right? So the filtering is done on the prism level, right?
Okay.
And when you have here your sensors, and we had sensors that were 1080p, 60 frames per second, right? So if you have 60 frames per second with filters, you would have to change that a lot.
Actually, you don't have to have it like a rotating filters. You can have a beam splitter and basically have them in parallel.
Yeah.
So this is like a beam splitter.
That's a beam splitter, exactly. Beam splitter, usually it's like a tube, and then each one goes out, right? So, so it goes up, right? And then at each level, different wavelength is, at each distance or whatever, a different wavelength is extracted from a different band, different color is taken out, right? But this is because our application had to be handheld application, right? The beam splitter is actually a little bit longer and a little bit bigger than this. This was actually fairly small, 2 fingers, not even that altogether, right? So it was a constraint that was basically agronomical and mechanical.
Okay.
That's why.
How would you filter in the prism?
In the prism, because this is not one prism, these are 3 prisms. And between the layers, there is a coating that acts like a filter.
So you have a bandpass filter there?
Yes, the coating on here works like a bandpass filter, right?
I know that like bandpass filter optical, sometimes they run into 32 layers of coating. There are some of them actually we go 32.
Well, for us, because we had optics before that, right? We actually measured how much there is a leakage between them, and the suppression between them was actually very was adequate.
How many coatings? How many layers?
I don't know. That I don't know.
Okay. Just for focus. Any more? Any questions, Dr.
Well, you're using CMOS. What's the difference between using the CMOS and CCD?
Well, if you asked me that like 5 or 6 years ago, I could say to you point blank, go for the CCD. But now the technology with the CMOS, it's comparable to the CCD, very much comparable. And the good thing about the CMOS technology is that CMOS is a semiconductor-based technology. So whatever you have your sensor is a CMOS. So basically, we just have a wafer of a CMOS, and behind it you can add any type of semiconductor logic. So it basically on one chip you can have, we had, for instance, the one that I had 16 ADCs. It had serialization, it had gain control, it had everything, right? Because of that, the CMOS are now really taking over, but that's only due to the really late development of them, right? But like I said, 5 or 6 years ago, I would say if you need something really where you have an environment that's starved for light, where the light is really low, I would say maybe go for CCD. Now I cannot say that anymore because CMOS, it's comparable. It's comparable, if not even better.
Okay, so, do you have any idea about the Fourier filters which you put in front of the camera and get the Fourier from the filters directly? And then you reach a great definition.
I use two types. One, I use the sensors that were monochrome, so everything, and I use the other ones that had a bare pattern on, right? So if those are the ones, those are the only ones that I used and I have experience with, because when you get a signal that's in bare pattern, you have to debar it, right, to get a complete picture. But beyond that, I don't know. Maybe if I hope you understood what I said. I hope that answered your question.
Okay, when you talk about the low light levels and you're talking about a CMOS sensor, there are other recent sensors. I forget the name now. These are these are actually they are very good for low light.
Yes.
Forget the name. If you remember the name.
There is, for instance, EMCCD.
Yes.
There is ICCD.
Yes.
But there is also now SCMOS, which is very much comparable. So, yeah, but please continue with that.
Yeah, no. So basically, what's the impact of? Are you using such sensors here?
Here I use just the well, it's not standard CMOS because this was the one that came fresh out of the oven from Sony. They were really pushing the technology that they just developed, because there are two types of sensors when you come to the imaging. You have them front illuminated and back illuminated, and those that are back illuminated are actually much better. They have their quantum efficiency, it's much better, and those are the ones that we use. Now when you talk about EMCCD and ICCD, they have an additional complexity in there where when the photons are collected, they go through something called the multiplier, which on the photon electron level is gaining up. I'll put it like that, but I shouldn't say that, but it's because it makes physically no sense, right? But engineering point wise, right, when it goes, what it does, it increases the signal such that you have high signal to noise ratio. Those, they are very big sensors still, and for the handheld application they would not be good. But where are they good is definitely in if you have benchtop imaging system.
I think they need cooling, if I'm not mistaken.
They do need cooling, especially the big sensors. They need cooling. They have a huge power consumption, and if they heat up, their thermal interference really takes down signal to noise ratio.
Thermal noise.
Yeah, thermal noise takes down signal to noise ratio, right? They have also the dark noise that's very hard. So you need, for instance, we had a Pixis camera that was cooled to minus 70 degrees, right? Because we were getting such a small signal, right? But that was a desktop thing. For a handheld thing, they wouldn't be, I mean, Pixis camera, you have to carry it in your backpack, basically. I mean, and you can't use that.
Okay.
Is the number of photons of the red, blue, or green the same number of photons inside the same number of electrons from the CMOS?
Red, green, and blue, what doesn't mean number of photons. It only means the wavelength. Yeah, it only means the wavelength.
Yeah, that's my question. If you have like 10 photons of red or 10 photons of blue, 10 photons of green.
Each manufacturer of the sensor provides the quantum efficiency of each band. If it's not that, then for instance, for the monochrome, they put for all the cells like some average value of the quantum efficiency over the whole range, and then you can, for that you can compensate.
Any more questions? Just curiosity, what was that image that you showed? Is it a tongue or is it
No, it was
it's
a mole. It was a mole.
A mold.
A mole on the hand that they didn't actually know what to do with it and what not to do. So that was a mole from the hand.
Anyway, it looks ugly. Any more questions? Then thank you very much for
Thank you for being
very
here.
interesting engineering.
Thank you.